Hi, folks. I'm Dex from Verilog Solutions. Verilog Solutions is a full-stack Web3 team. Before we start, we should take the opportunity to thank the Remix team for inviting us to this event. And I want to make a short introduction about for my teammates. And while I make the introduction, you can follow us on Twitter. So I'm Dex, and the business development lead at Verilog Solutions. Daniel here, he's our audit lead. Zoe is our research lead. Professor Zehua Wang at UBC is our chief scientist. And Rishi, he's our senior auditing engineer. And he will be the one that walks you through one of the cases we prepared for today. So today we prepared 3 different puzzles for you. And you can get those puzzles by visiting this GitHub link. And don't worry if you missed it, because we're going to share the deck in the Discord channel very soon. And the very first puzzle is very classic re-entry state attack. And I really want to thank my teammate for preparing this demo. And now I'm going to hand it to Rishi to walk you through one of the puzzles.
Hi there, I'm Ray. Thank you very much, Dex. So as Dex said, I have 3 puzzles for you. So you can just find it in the GitHub repo that's shared by our teammates in the channel. So let's go here. Okay, so all of our puzzles are located in the Solidity puzzles folders. Open these folders and then go to the contract folder. You will find all 3 puzzles. So as it says in today's section, I will walk you through puzzle 1. Well, you are more than welcome to get your hands on the second and third one if you think the first one is too easy for you. If you have any questions, go to the Remix Game Day Discord channel or follow us in our Twitter. We're more than happy to answer any questions. So let's jump to the contract step. So as you can see, our aim here is to attack this poor victim 1 smart contract. So victim 1 smart contract is actually a very simple DAO or bank smart contract, which has only 2 functions. The first function is to deposit Ether into that smart contract. So this smart contract takes the amounts that you enter and store it into its own wallet. So this is how deposit does. And the second functionality is to withdraw. Withdraw means that you can take all the money you store into this victim smart contract back to your own wallet. So it seems like pretty simple and there's no much space to attack it, right? But the reality is that you, of course, can hack it. We have a transaction recording that captures the whole process of a hack. So maybe I can play it here for you. And of course, you can do it by yourself in your own Remix IDE. Everything is on the Remix IDE without any like external node or something. Let's go to the transaction records folders and click the puzzle1.json file. Be sure that this JSON file is the active tab in your Remix editor. And then we go to the transaction recorded and click this play button. So here in the Remix console, you may see that there is a bunch of transactions pop up. So where shall we start? Maybe we can start with the very first transaction in the console then. Let's look at it. Okay, here we are. So transaction number 0 is the very first transaction that we send into in this transaction recording. So what did it do? So if we look at the types and input, we may find that this is actually a call to the constructor of this victim 1 smart contract, which means that this is actually the transaction to deploy victim 1 into our BVM. And there's also a noteworthy thing that we also put some value into this deployment transaction. The value is 0.3 ethers, which means that 0.3 ether will serve as the initial supply or initial deposit into our victim1 smart contract. All right, then maybe we can skip the following transaction and fast forward to the actual attack transaction. Here we goes. Okay, here transaction number 4 is the attack transaction. This attack transaction is made possible by calling a external smart contract. Here we call them contract attacker. And the interface that we call, it is a attack interface. This transaction also takes some value as the ether that the attacker passed to the attacker contract. So the value is 0.1 ether. And let's look at the result of calling this attack transaction. We have a pretty straightforward log here. So we can first look at first line of the log. We can find that there's actually 0.4 ether in the victim smart contract app. So where is this 0.4 ether came? So this came from 0.3 ether that we initially deposited into the victim smart contract plus the 0.1 ether that the attacker contract deposited into the victim smart contract. But in the end of this attack transaction, we can find that the remaining balance in victim smart contract is only 0.1 ether. So the difference indicates that the attacker managed to use only 0.1 ether to take 0.3 ether out of this victim smart contract. This is like not legitimate, right? So how can an attacker do this? What is happening? To answer this question, we must have a look at the implementation of the attacker smart contract. Let's browse for the attack function in the attacker smart contract. Here we are in line 31. We can find there is the attack function. So there's only two things that is done by the attack function. The first thing, take that 0.1 ether and store it into victim smart contract by calling deposit. Well, this is pretty simple. There's no much space for you to start the attack. The attack starts in the second line, the withdraw function. So the tricky things here is that the attack function passes the attacker contract address itself as the parameter to the withdraw function. And then all the control will be handed to the victim smart contract. And let's deep dive into the victim smart contract to look what is going on. Okay, here we go. In the victim smart contract, we go to the withdraw function here. The parameter is the address to the contract attacker. So line 1, line 37, is getting the amount that deposited by the contract attacker. So as we said, the value is 0.1 ether here. So the amount is 0.1 ether. And in line 36, right after line 35, the victim smart contract transfer all the 0.1 ether back to contract attacker's wallet. So this is made possible by invoking the call instruction in Solidity. So there's a quick reminder. So remember that if you are sending some ether to a smart contract, you will always invoke the callback function if you do not specify the correct API. So our attacker smart contract happen to have this kind of fallback function, which is called receive in his definition. So after this call, the victim then hand over the control back to the attacker's receive function. And inside of the receive function, the attacker do an evil things to call the withdraw function in victim once again. This means that the attacker can go back to the victim smart contract, which we call them re-enter as a widely used terminology. So this time, attacker re-enter victim smart contract, and we are back to line 34. And in line 35, we can find that, okay, this time the victim trying to calculate how many ethers you remained in the deposit, because the update to the amount happened in line 38, and we haven't processed to this kind of update yet. So the amount is still 0.1 ether at that time. So the victim will perform a second ether transfer back to the attacker smart contract, and this time it transferred 0.1 ether. So let's wait a minute, wait a few seconds at this moment. So remember that this is the second time that the victim sent that 0.1 ether to the attacker contract. However, this is not supposed to be happen for the second time, because the attacker only stored 0.1 ether in victim, right? So this is how the bugs goes, and if we go back to the attacker's receive fallback function, we may find that this loop will continue again and again until the attacker smart contract be able to drain all the ether. I mean, drain all the ether other than that 0.1 ether out of the victim smart contract. So this is the internal transaction or re-entrance trace of this kind of re-enter attack. So here, if you are interested in some low-level detail, like EVM representation, you are more than welcome to go to the debugger in Remix, and it will grant you access to the stack and storage and memory things. It will be a fascinating feature. So how do we protect our smart contract from this kind of re-entrant vulnerability? So one very simple walkthrough is to take effect before we interact with our smart contract. So remember, line 38 is where we take effect. Our effect is to set the amount back to 0. So if we move this effect statement to a place before the interaction, before the call instruction, it will first set the amount to 0. So when the attacker trying to re-enter our updated smart contract for the first time, because the amount has already been set to 0 in the first time, so the amount is 0, and the attacker can no longer withdraw his 0.1 ether from the victim smart contract. You can also use re-entrant guard from OpenZeppelin to protect your function from being exploited in a re-entrancy hack. That's also a workaround. Okay, great. Everything sounds great here, and we also prepare some hard hat unit tests and remix unit tests if you want to come up with your own attack. So here we have in the test folder, and we can see there's JS test folder and Solidity test folder. So Solidity test folder, we can have, there's 2 tests in Solidity. We can run it in the Solidity unit test plugin, just type the path to the test folder. So the test. Yes, we may see that there are like 2 tests pop up in our like in this like window, and we click run. Oops, maybe it'll be fine. Oops, sorry, I configured wrong like compiler version. Choose puzzle 1. Let's run it again. Okay, we can see there. So this is a test to the attack smart contract. So if you like write your attack interface successfully, our test will pass through your smart contract then. So this is a demo, a very quick demo to the first and easiest puzzle. For the second and third one, they are like much harder. So take your time. We also have like walkthrough and user manual in the GitHub repository link that we share in the Discord channel. So again, if you have any questions, feel free to reach us via Discord or Twitter, and also you can ask it like here. Thank you so much, and we are happy to answer any questions.
Any questions? Okay, well, Rui, can you hear me? Maybe you can't.
Yes, I can hear you.
Oh, okay.
I just mute myself.
Yeah, it looks like there's no questions, so thanks so much. And if there are questions later, you can ask them in the Discord or ask them specifically. Thanks so much. Talk to you guys later.